So, CH4O, remember, save the hydrogens for last. They're always just going to kind of decorate the outside of your molecule and make sure that everybody's happy with their complete octet. So I'm going to first put down my carbon and my oxygen. Then I'm going to decorate it with the hydrogens. We said that carbon needs 4 bonds. So I'm going to put 3 hydrogens over there. And I got 1 left over, which is great because my oxygen needs 2 bonds. So I can put that one over here. All right, and again, oxygen should have those 2 lone pairs on them. So now we got CH6N. Again, save the hydrogens for last. I'm going to make carbon have its 4 bonds. Okay. Now I get to my nitrogen. Nitrogen likes to have 3 bonds and 1 lone pair. But remember, when we say it likes to have, that's its most stable form with a formal charge of 0. In this case, I can tell by my molecular formula that we have a formal charge of +1 here. So instead of just having 3 bonds, my nitrogen's going to have a total of 4 bonds. Okay? And this structure is not correct quite yet. You have to explicitly put that formal charge on that nitrogen atom, right? So I need a plus sign on that nitrogen atom to be correct. And if nitrogen does have this formal charge of +1, it's not going to have any lone pairs associated with it, so that's that there. Okay. We made these cheat sheet charts for these other elements, and they sort of had some similar patterns, so I wanted to see who was able to fill it out based on just, by analogy of what we saw before. Fluorine, in its most stable form, when it's got a formal charge of 0, it has just 1 bond and 3 lone pairs. Okay? If I'm going to fill out this column here where it has a formal charge of -1, right? I need more electrons on that fluorine atom, right? So it's going to increase in the number of lone pairs and decrease in the number of bonds. So this would be a fluorine that has 4 lone pairs and 0 bonds associated with it, right? This is the fluoride ion. This is what's in ionic compounds like sodium fluoride, is just this ion here. And very, very seldom, but every once in a while, we do see the halogens with a +1 formal charge, and then everything's going to trend the opposite direction. I'm going to have 1 extra bond and 1 fewer lone pair. So fluorine has 2 bonds. It has a positive formal charge. Okay? All right, so now we get into the fun stuff here. Today we're going to be learning about 2 new structural representations that are used quite often in organic chemistry. Okay? The big problem that we see in organic chemistry that you don't have so much when you're talking about ionic compounds is a formula like C5H12 refers to multiple different molecules, each with their own distinct chemical properties, different boiling points, melting points, different reactivity, all that jazz, right? This in and of itself is not enough information for me to know what molecule I'm talking about. So in organic chemistry, we like to do structures. That's why we started with Lewis structures. But Lewis structures kind of are a pain in the butt. They take a little bit to draw. You're always drawing like 45,000 hydrogens at the end of it, right? So we have sort of a shorthand that we use. The first one is something called a condensed structural formula. And these are kind of like your molecular formulas, but they give you more information about the actual structure of the molecule. And unlike the next sort of structure that I'm going to show you, the important thing that I want you to know about these condensed structural formulas is we need to be able to read them. I'm not so concerned with you writing condensed structural formulas. It's much easier to just draw structures. But what you're going to see is this is a way of representing a structure all in one line of text, which means that it's the favorite thing of textbooks and computer programs and stuff like that, right? Just a simplified way to write things out all in one line. So you will see them often in your textbook. We need to be able to read these things when we see it. All right, so let me give you an example that I think you guys would be able to kind of pick through just on your own here. A condensed structural formula, again, something like C4H12 H10. That's not enough information. But I could have, and very similar, CH3, CH2, CH2, CH3. This would be an example of a condensed structural formula, and this points me to one unique structure here, right, where these carbons are all sitting all in a row. So if I'm going to translate this to a Lewis structure, it's just my 4 carbon atoms connected. Each one, the end has 3 hydrogens. The ones in the middle have 2. And then lastly, my N1 also has 3. Whoops. Okay. So here is our Lewis structure. We were drawing those a bunch last class. This is the same molecule, but represented in what's called its condensed structural formula. Okay? All right, whoops. So, that's all well and good when it's just sort of a straight chain molecule like that. It's pretty straightforward. Now I'm going to show you some of the trickier ones to read here. One of the ways that we can represent really large molecules is by using parentheses. So if I were to draw something like CH3 and then in parentheses CH2 with a 5 on the outside, CH3 here. Okay? These parentheses are telling me that I have multiple CH2s. So I have 5 CH2s in this formula here. So everybody take a second and draw me the Lewis structure of this molecule. So I got my CH3 on the end. And now I have to put 1, 2, 3, 4, 5 carbons, each with 2 hydrogens in the middle. And then finally one last CH3 on the end. All right, so I have a total of 7 carbons in this molecule here. All right, so we can see our parentheses with this little subscript on the outside, and that just means we have more than one of whatever it is in those parentheses. All right, so do another one for me real quick. This is going to be CH3 to CH2. Bless you. Okay, now be careful. Before we had CH2 in parentheses, right? So that's in the middle of a molecule if it's a carbon with 2 hydrogens. CH3, I can't put down one CH3. Well, I put down one, everything's all good. If I put down another CH3, I'm done, right? I don't have this other carbon and hydrogen on here, right? So these CH3s, these are what we call methyl groups. They're always sort of sticking off on the end. So in this case, I need to have one carbon. Let me find my eraser. Both of these CH3s are attached to this carbon right here. The most important rule for when you're drawing your condensed structural formulas is just don't forget all those rules that we talked about with carbon needing 4 bonds. As long as your carbons have 4 bonds and your hydrogen has 1 bond, you're sort of set correct, right? So just don't forget about our rules for this sort of thing. In this case, I have one CH3, okay, attached to that carbon, and another CH3 attached to that carbon. I don't know why I drew it in a straight line like this, but anyways, you could rotate it 90 degrees, same thing, all right? But yes, and so you can see there's kind of more than one way to represent a molecule within a condensed structural formula. I could have said CH3, CH2, CH3, that would have been perfectly equivalent. So there's not always one right answer. Again, my goal isn't to have you be able to write, look at a molecule and write the condensed structural formula, because again, you can kind of write it multiple ways. The important thing is you're going to see these written in your textbook and in your homework system problems and stuff like that. It's the preferred method of a computer because it writes everything all in one line, right? So being able to read these is really important. All right, so now let's do a few more here. This is going to annoy me taking up a bunch of room, but whatever. So now let's see something like this. CH3, CH, in parentheses, OH, CH3. So this is another use of parentheses that you see in these condensed structural formulas here. Right? There's no little subscript on the outside. It's just one group of atoms. This means that it's sticking off of the main chain. So it's kind of pointed out separately from the other carbons in this molecule. Okay? All right, so let's just do this one together, and then I'll show you sort of another example of something similar here. So again, I'm going to start with just drawing my CH3, my first one in my line. Then I have a C with just one H. And then I get to my next group, and it's in parentheses here. So now it's going to be sticking up off of that main chain. I'm going to put in my lone pairs to be good. And then my other CH3 on the other side. It's called an alcohol group. We'll talk about functional groups here in a second, but yeah, we're going to see a lot of functional groups here, and then we're going to start putting names to these different combinations of atoms. All right, so let's do another one that's similar to this. CH3. That can live there. That's fine. All right, so now we're going to read them from left to right here. C with 3 H's, C with 2 H's, C with just 1 H, but then I have that group in parentheses, which means that it's sticking off of this main chain here. So N, H, H. If I'm going to be really good, what am I going to have to complete here? The lone pairs. Awesome. Now another CH2 and CH3. Cool. All right. Let's do 2 more here, or a few more here. I want to point out some sort of common groups of letters that you're going to see, and they usually correspond to the same sort of similar structure here. So CH3 and then CHO. Everybody see if you can't build this molecule here, remembering your octet rule and number of bonds and all that jazz. All right, so let's just look here. It is very likely that you may have gotten stuck here, so let's just see. Let's see if we can't reason what's going on. So I got a CH3. Boom. I got another carbon. It's got a hydrogen and an oxygen, right? What's the problem with this carbon on the end here? It's all sorts of mad. It's only got 3 bonds. What's wrong with my oxygen? It's only got 1 bond, right? It's also all sorts of unhappy here. So they need more bonds, but I can't just go in and put some hydrogens on there, right? I mean, my formula very clearly states that I only have 4 hydrogens in this molecule. Well, don't forget, we can always, what is it? Double bond, exactly. You can always just increase your bond order here. So in this case, if I have a double bond between my carbon and my oxygen, and this is a sort of grouping that you will see often in molecules, CHO, and it always represents a carbon that is double bonded to an oxygen and then has a hydrogen sticking off of it. So that's just sort of this grouping of atoms that you're always going to see together that represents what's called a functional group. Okay? Similarly, let's do another one, CH3COOH. So I'm going to start with my CH3. Notice how we're always starting with CH3 for the most part, because that's what a terminal carbon would have, was 3 hydrogens around it. So then I have another carbon, and now I have this OOH to deal with here. And I think it would be pretty natural to kind of just put them all in a line here, but we got a big problem. Actually, my oxygens are happy, but my carbon is very unhappy with its one bond here. So this is not how we're going to be able to arrange these. Instead, both of these oxygens are going to be connected to this carbon. Okay. I could put the hydrogen here, but now my oxygens are mad. So I'm going to move it over here, and this is on the right track, but I got to do one thing. Does anybody see how I can make that oxygen and carbon happy? Double bond again, exactly. So, and this group right here is a super common functional group in organic chemistry. It's going to be one of the first ones we get introduced to. COOH, representing a carbon double bonded to one oxygen and then single bonded to another. This is an organic acid. They almost, they very often share this functional group right here, this acidic functional group. So we're gonna see this a lot. We talk about acids and bases as like our first set of reactions here. So we'll see this next week. All right, and then one more here, let's see, CH3CO, CH3. Right, so CH3, C, it's got that oxygen on there. Again, I have this similar problem that we've run into where if I just leave it as a single bond, my oxygen is mad, my carbon's mad, but we can solve this pretty easily by making it that double bond. Okay? And I think it'd be natural to be like, well, hey, it's sticking off the main chain. Why don't you put that oxygen in parentheses? Because it's just that single atom, and it's implied that it's sticking on in that double bond because there are no other hydrogens on that carbon, right? So the only way that you can make everybody happy is with that double bond, okay? But again, you'll kind of see these similar signatures over and over again. A CO all by itself just represents that carbon-oxygen double bond. This is going to be another really, really important functional group that we see in organic chemistry. Okay. All right, so now to the fun part. And I know that was already so much fun, but now we're going to get to what are called bond line structures. Other places call these skeletal structures. I learned it as bond line structures, so that's what I'm going to stick with. All right. So I'm going to leave some space because we're going to make some notes here, but let's just put down an example and kind of pick it apart here. I think it's going to be easiest to sort of learn by analogy here. So let's put down these 3 carbons. Okay, so this is the perfectly legal Lewis structure for this particular 3-carbon organic molecule here. If I wanted to represent this as a bond line structure, I would just draw these 2 lines here. So these are representing the exact same thing. Okay, so in our bond line structures, what we're going to see is there are no C's and H's written, right? So in bond line structures, carbons and hydrogens are implied. Actually, I'm going to say carbons and their hydrogens are implied because we do explicitly write some hydrogens. Okay, so then how am I supposed to look at this zigzaggy line and figure out what the heck is going on? Okay, carbons are at the end points. I don't know how to spell. And intersections in our bond line structure. All right, so what do I mean by that? I mean at each of these endpoints of my line segment, this corresponds to this carbon here. This corresponds to this carbon here, right? So the end point of these line sections, they represent carbons. And the intersections of these line segments also represent a carbon. So where they meet in the middle here, that's my middle carbon. All right, so within my bond line structure, the location of these carbon atoms is implied, and they are located at the end of all of our line segments and at any intersections of our line segments. All right, so then what about hydrogens? Hydrogens are on each carbon. And how do I know how many hydrogens there are? How many hydrogens would have to be on this pink carbon here? Well, enough to give it its complete octet, right? Enough to make up those 4 bonds. So you know just by looking at how many bonds are already explicitly written, how many hydrogens you need to put down to fill everything out, right? So the position of those hydrogens are implied. They're located on each carbon in order to complete its octet. All right, so let's do another one here. I'm going to put down this bond line structure. All right, and I want everybody to take a second and give me the molecular formula for this compound. How many carbons do you see? How many hydrogens do you see in this molecule here? All right, C what, H what? All right, so I'm going to go through, and this is going to be one of the most important skills that you're going to learn in this course, and it's going to be the best double check that you can do after you get done with a problem to make sure you didn't make a simple mistake, and that's to count carbons. You're going to see me up here tapping away at my screen all the time because I'm counting carbons in these bond line structures. And again, I'm just going to count because they're at each endpoint and intersection. So 1, 2, 3, 4, 5 carbons here. All right. So C5, and then in order to get my hydrogens, I got to go through the ends, have 3, and each one in the middle here, since it already has 2 bonds, will have 2. All right, so 3, 5, 7, 9, 10, 11, 12. So C5H12.
When writing out the formula, it's okay to put them both in like the parentheses brackets to just like condense it further. So like CH3 to CH23.
you could have, you know, I was specifically asking for the molecular formula here. If you had done CH3, CH2, 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 CH3, or CH3 in parentheses CH2, 3, CH3. Was that your question?
So like just running like this. Is that a lot or no?
This one actually wouldn't work out. You'd have to put one on either side here because this sort of implies that they're both attached to the same carbon, and then you're going to get to a situation where you don't have. So this is how you would have done that. Okay. But importantly, this is the molecular formula here where you're just counting the number of each. And that's the first thing I'm going to ask you to do in your homework is here's a bond line structure. Tell me how many carbons and hydrogens you see, right? That's kind of the first skill that we need in looking at our bond line structures. All right, let's do another one. We did some pretty easy ones. Let's throw some branch points on there. So I'm going to count all my endpoints and my intersections for a total of 6 carbons. Hydrogens, I got to figure out, so all these terminal carbons here each have 3. All right, what about this one right here? How many carbons, how many hydrogens should I put on that? Just one, right? It's got 3 bonds that are explicitly drawn, those carbon-carbon bonds, but it still needs that 4th. So each one of these also has it. All right, so C6H14.
So for the 2 carbons in the middle, we can't just double bond those 2 together to complete octet?
Okay, so there could be a double bond there, right? But when I gave you that structure, I showed you that it was just a single bond. So you can't be throwing extra bonds on the page at that point, right? I'm telling you this is the molecule, show me the formula. Yeah. So you can't adjust that structure of that molecule. So we'll do an example here in a second where you would see what a double bond looks like. But if I give you this structure and I say, what's the formula here? Don't start adding extra bonds because then you're changing the number of hydrogens, okay, right? So bottom line is if you see this single bond here means that there has to be additional hydrogens on there. All right. And then one more sort of branched molecule that we can see. Notice how, let me actually just redraw this real quick. We do these, you'll see these sort of like squiggly lines here. And if there's another one, they come off and everything's all spaced out nicely with 120 degrees. That's all well and good. If you do have 4 bonds on that carbon, there's sort of no nice, neat, easy way to do it. So then we put them 90 degrees apart, okay? So for example, everybody take a second, tell me what the formula of this structure is here. All right, endpoints and intersections, right? Just follow the same logic that we've been following. I know it looks a little funky compared to the other ones that we've seen, but exact same logic needs to be applied. All right, so again, my endpoints, 1, 2, 3, and my intersections, so that means this intersection right here also represents a carbon. All right, so that's 1, 2, 3, 4, 5, and 6. So C6, go in with our hydrogens, 1, 2. Whoops. And then how many should I be putting on this intersection right here? None. It's already got those 4 bonds, okay? So that one's not going to get any. This one needs 2 more. So this would be C6H14 as well. All right, and again, that's why that molecular formula isn't really telling you much. We had 2 completely different molecules here, both sharing that same formula. All right? All right, so now let's look at some higher order bonds. How do we represent double and triple bonds? So here's my 4 carbon with all single bonds. If I wanted to represent a double bond between those middle 2 carbons, I would just put an extra line there, right? So that's just how I would represent double bonds in our molecule. One of them's kind of floating out a little bit separate, but that's how you'll see this pictured. Everybody take a second and give me the formula for this molecule here. Same logic as we were doing, but now remember that those 2 lines mean that you have 2 bonds between those carbons. All right, so first of all, how many carbons? 4. Right, so every endpoint and intersection, C4. If I'm putting in my hydrogens, again, these N ones need 3. But what about those double bonded carbons? How many hydrogens does each one of those need? 1. Just 1, right? So here's 1 bond. Here's a second bond, and here is your third bond, right? That double bond is 2. So I only need 1 more in order to complete the octet. So C4H8 would be my formula here. Okay? And triple bonds trip people up the most. So let's just put down a compound with a triple bond. Whoops. All right, so everybody look up here for a second. Let me show you the big mistake that people make when they are counting carbons and understanding structures with these triple bonds. Is they say, okay, I have 1, 2, 3, 4. I have skipped over a carbon, and this is really easy for people to do. That triple bond exists between two atoms, right? So on both sides of that triple bond is a carbon. So we're going to make a note specifically so we don't get messed up in the future. Don't forget that there's a carbon on both sides of your triple bond. So that's a really easy mistake to make. The other thing that's weird about triple bonds is notice that I did not draw this with my triple bond and then a kink, something like that, right? Let's think about why that is for a second. This is wrong, and actually your homework lets you get away with it. I'm gonna yell at you if you do it on an exam, okay? This right here, let's look at this carbon. What's the hybridization on this carbon? Everybody take a second and see if you can't remember from last class. Now that we're looking at bond line structures here, how would we figure out the hybridization of that carbon? It's just sp. And what is the geometry of an sp hybridized molecule? Linear, right? So that's why we draw those three atoms, these three atoms here. 1, 2, 3 are all sitting in a straight line because of the geometry of a triple bond. Triple bonds always have a linear geometry associated with them. So that's why we don't get to draw it in our little checkered pattern here. We have to draw them in a straight line for our triple bonds. All right, I'm just going to redraw my structure so we can finish this off. All right, and don't forget carbon on both sides of our triple bond. How do you spell triple? Ellie? Yeah, spelling, not my strong suit. Just let it slide if you see something completely mangled up there. All right, so as we had said, we went through and counted. We have 1, 2, 3, 4, 5 carbons in this molecule. C5. Let's put in our hydrogens. How many hydrogens should go on this carbon here? None. It's already got its 4 bonds. And what about on the end here? I need 1. Yep. So there's going to be 1 hydrogen sticking off the end here. So C5H8. Yeah. Okay. All right. So now let's look at another one here. We said that our carbons and our hydrogens are implied. All other atoms are not implied. You would explicitly have to draw an O if there's an oxygen in your molecule, or an N if there's a nitrogen, or an F if there's a fluorine, all that. It's only carbons and hydrogens that are implied. And it's only the hydrogens bound to carbon that are implied as well. So this oxygen isn't just going to be like that. I'm going to put that H on there. And actually, I'll do it like you do in your homework system. You have to put the bond in as well. Okay. What's my oxygen missing, just to be good? It's lone pairs. All right. And so maybe just look up here for a second, and then we can do a few on our own. If I'm going to count carbons here, I have my endpoints and my intersections, but there's no carbon over here, right? There's an oxygen on the other end of that bond, which is explicitly represented. So in this case, I still only have 4 carbons in my formula, right? If it isn't a carbon, it will be explicitly represented. So on the other end of this bond here is that explicitly represented oxygen. So filling in hydrogens, 1, 2, 3, 4, 5. Put these 3 over here. How many should be on this carbon? 1, right? It's got its 3 bonds represented. That means it's missing 1 for my hydrogen. And one thing I just want to caution against, don't forget when you're counting hydrogens, I have 3, 5, 6, 9. Don't forget the one that's also explicitly represented here, right? So there'd be 10 hydrogens total in this molecule.
We split that H with the other H's in the molecular formula too?
So a molecular formula can be sort of as condensed as you want, right? So there'd be 2 perfectly equivalent ways to do this. You could say C4, let me just 6, 7, 8, 9. You could see C4H10O or C4H9OH. Both of those are perfectly fine. You will see in our organic chemistry, we kind of like to hint at how the atoms are arranged. So it would not be uncommon at all to see like an OH there or whatever. Molecular formulas, though, can be just super condensed. Often, and what I'm going to ask you for is just counting how many atoms are present. And really, you actually wouldn't see this too much because it doesn't give you enough information about where that OH is located, right? So if you're going to do the real structure, condensed structural formula, then you want to do something like CH3, CH2, CHOH, CH3, okay? It's not to say that this isn't like, you know, all they really have to do is total up to the correct numbers, okay? But yeah, it doesn't quite have enough information to be useful. Okay, cool. So then you're going to give me the molecular formula for this thing here. All right. So counting up my carbons, 1, 2, 3, 4, 5, 6. How many hydrogens do we have? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? Don't forget the ones that are explicitly represented as well. And then my 1 nitrogen. Okay. One other thing, let me just show you up here real quick. I am explicitly drawing out those nitrogen-hydrogen bonds because that's what you're going to be doing in your homework. it would not be unusual to just see this same functional group represented without those sticks there as well. And we're going to kind of gravitate to that more shorthand as we go on throughout the course. For now, I think it's important to draw these bonds and these lone pairs as we're getting started. Okay? But yeah, you will see that sort of shorthand as well. All right, and then this last one here is kind of weird because now this oxygen is sitting in the middle of a molecule. This is a functional group called an ether. They're pretty boring. They don't really have very many fun reactions associated with them, but nonetheless, we'll study those. But just to sort of point out what it looks like here, and if we're going to go through and count carbons, we got our end point and our intersection, but there's no carbon here, right? That is taken up by that oxygen atom instead. So in this case, there are 3 carbons, 8 hydrogens, and 1 oxygen. Cool? So we can look at a bond line structure and kind of make sense of what we're looking at now. All right, cool. So then I want you to draw one for me here. I'm going to give you this Lewis structure, and you're going to turn it into a bond line structure for me. All right, so I have 3 carbons in this molecule. So I need to go, right, as soon as you put down a line, that's 2 of them. So here's my 3rd carbon here. But then since this is what we call a heteroatom, something that's not carbon or hydrogen, it has to be explicitly represented with its own bond. And we're going to be good and put our lone pairs on there as well. All right, so that's how I would get. And just to sort of color code so we see what's what, this carbon's this carbon's this carbon is this, and of course here is my fluorine. Okay, so now in this molecule here, we have a triple bond But remember, we're going to be really good when we draw our triple bonds, and remember that all three of these carbons are sitting in a straight line because of the geometry of those triple bonded sp hybridized carbons. So my next bond here isn't going to go down here. It's got to go up in a linear fashion. Let me actually get rid of my colorings here so we can see. Boom. Right. Here's one carbon. On the other side of my triple bond is my other carbon. And then finally that one all in a line. And I got to put one more on there rather. And then I'm done. What am I missing? The chlorine, right? The chlorine's got to be explicitly represented coming off of this green carbon that I colored. Boom. Okay. Yeah.
Is that the only way to try, or like this is wrong?
It's on the wrong carbon. So look, 1, 2, 3 carbons. It has to be on this carbon here, right? Yep. So the structure wasn't wrong, but it does have the chlorine in the wrong place. It could have been a perfectly legal structure, just not the one that I had started with. Okay, so then to end things off and kind of tie everything that we've been talking about this week together, I'm going to put down this formula, C4H10, and you're going to draw me the bond line structure of the molecule that corresponds here, and there's going to be two different structures that you can draw. I want you guys to see if you can get both of the structures that have that same molecular formula there. All right, so first of all, always the easiest one to get is what we call the straight chain, where all those carbons are just lined up all in a row, right? 1, 2, 3, 4, boom, okay? But there is a second structure that I can draw that has this same formula here, all right? And I'm gonna give you a hint, it's just not in a straight chain. There's gonna be this branch point where you have a carbon that's bound to 3 other neighbors, right? So in my mind's eye, if I'm trying to get this next one, I'm going to think of like, okay, well, I'm going to pick up this carbon here, and I'm going to move it around to somewhere else in my structure, right? So if I move it from being on the end to over here in the middle, that's how I can get my second structure out of here. So the other bond line structure with this same formula would be this one here. Both of them have the same number of carbons and hydrogens. This is what we call a straight chain. And this one we call a branched chain. And depending on the formula, you can have a bunch of different branch chain molecules. The more carbons you have, the more possibilities there are out there. All right. So last thing I'm going to make you do for me is now I'm going to give you this condensed structural formula. And you're going to draw me the bond line structure of this molecule. right, so I'm going to first do the Lewis structure so that we could maybe see all three of these representations all next to each other. Remember that COOH is this pattern we'll see a lot where carbon has one double bonded oxygen and one single bonded oxygen. Then I'm going to take this, if I'm going to do my bond line structure, now I don't have to explicitly represent those carbons and hydrogens. So boom. But I do have to represent those oxygens and any hydrogens that are bound. So I'm going to have a double bond to one oxygen and a single bond to another oxygen. And I'll be good and put in that bond. Cool? All right, at this point, you guys know your organic chemistry ABCs here, how we just draw and look at structures, because again, that's going to be so important in this course is how these structures change as we do reactions with them. Okay? Cool. Okay, so let's do this first one. And I'll sort of color things so we can make sure to put our nitrogen in the right place. I'm going to draw my 2, 3, 4 carbons. And I need to make sure that my NH2 group is sticking off of the pink one. And am I going to point it down here? No, right? We want these all to be spaced out evenly, so it's going to be pointed up and H, boom. Okay? I'm drawing out these nitrogen-hydrogen bonds here because that's what you're going to be doing in your homework. When we start out, we're going to kind of do it the long way here. Eventually, we're going to be able to simplify things. You know, this group here would be sort of more compactly represented as just NH2, and that's a very normal way to see it as well. But when we're first getting started out, we're going to draw those bonds in.
Would it be wrong if, like, your first line, instead of going, like, upwards where you have the nitrogen, it was going downwards just because of that space? Like, I started doing it your way, and I thought it would be wrong if I made it branch up, so I kind of flipped it.
So like this?
No, that's,
Or you're
so
saying
the
like the
first
whole
line-
molecule is flipped up, so then you're
Kind
saying
of,
sort of
yeah.
like this.
I went downwards first. I started from top and went down. Yeah, so I can make it branch up to the bottom.
That's the exact same thing.
Okay.
Yep, that's perfectly fine. Whether you start your zigzag pointed up or pointed down doesn't matter. Okay? The other one isn't even like, I don't know how to say it. Like your homework, let's say that you did do it like this. I think your homework system would still accept it because technically everything's still connected correctly and all that sort of stuff. The problem is it looks really weird, especially to somebody who studies organic chemistry and looks at these things. Like nobody would ever draw it like that, right? It's like if I asked you how many brothers you had and you told me you had 4 halves or something, you'd be like, what? You gotta sit here and do some math and fit, like, no, that's not how we talk about that sort of thing, right? So some of it's just kind of like standard convention and what looks normal and how we do things is to space things out. So yeah, no, we don't want to do that. All right, so this one, now I have 3 carbons. With that bromine on the end, I have to make sure to draw out with its lone pairs. Okay? Cool. All right, so now let's do some with double and triple bonds. Make sure we got that down to draw. Yeah. No, this is not. Where your floating line is? Yeah. So we have these 3 carbons in a row here. So I'm going to draw my 3 carbons. Those first 2 have that double bond between them. And then my green carbon has a chlorine sticking off of it. Okay, now good question over here. Does it matter whether I put this like floating line segment on this side or this side? No, not at all. All right, you just need to have 2 lines there. All right, and again, the triple bonds are a pain because we got to remember that all 3 of these carbons here are sitting in a straight line. So I have my triple bond, right? That'll be between this carbon and this carbon. But my next carbon I have to draw in a straight line away, right? And then 1 more pointing down. So just to kind of continue my color coding here. Okay. And then that blue carbon also has that double bonded oxygen on there. So I'm going to put my double bond, but because it's oxygen, I got to explicitly draw that O in there. Okay. All right, so do these like bond line structures look kind of weird? Probably at first, but now that you can kind of read them, now that you know that all you got to be looking for is where those carbons are and how they're connected, right? This is how we're going to be representing our structures going forward, because how much quicker is it to draw one of these than a Lewis structure, right? It's just a convenience factor.